Hello and welcome back to the course. So we're gonna start talking about simply connected domains. It's section 4.3 in the book, and we're gonna cover the first half of it today. So what are we talking about? We're talking about simply connected domains. And so we make a definition. It's actually the wrong definition. We're gonna say a little bit about that in a moment. Why is this the wrong definition? But this is going to be the definition for us in this course. It's not that wrong. It works for domains in C. So all right. So how do we define this? We say a domain is simply connected if every cycle in U is homologous to 0 in U. Right? So that's what we mean by simply connected domain, right? So this is just stating it, exactly, right? So the winding number is 0 for every P in the complement, right? That's just the definition of homologous to 0, right? So examples. So this is an exercise. So in a star-like domain, for example. So, for example, C itself, doing a disk, the upper half plane, all those are simply connected. On the other hand, C minus the origin is not simply connected, right? There exist cycles in C minus the origin which are not homologous to 0. For example, the circle, right? As you probably know. Now, a couple of remarks about this. One of them I've already made. This is the wrong definition. It's not the right definition. Don't go to a topologist and say, this is the definition of simply connected. This is not the definition of simply connected. This is kind of the definition of simply connected. So it happens to work in the setting where we're doing it. And it's wrong for two reasons. The main, the first reason that this is not correct, the main reason, is that we're doing it in terms of homology and not the homotopy. And it really should be in terms of homotopy. Now, that's done in an optional section in the book. So you can look in the book and there's the right definition of simply connected, right? So sometimes we might say simply connected in the sense of homology or in the sense of homotopy. But in this course, we're not going to cover the optional sections. So we're just looking at the homology version of this. So that's why it was the first reason why it's wrong. So as I said, we could say simply connected in terms of homology, but we'll just say simply connected. Now, the other reason why it's wrong is that we define cycles as piecewise C1 instead of just continuous. Now, that's fine because we're talking about domains, so open sets, and so any continuous continuous path, it's approximately a C1 path. So we should be fine with that. So those are the two reasons why this is wrong, but we're going to take this as our definition, and it works for domains in C. So it's fine with that. All right. Now, the last bit about this definition: can a disconnected set be simply connected? And I want to claim ignorance on this. Because I've even asked topologists and they're not quite clear on this. Some places make this definition for even disconnected sets. It really depends, and there you would have to really get into the weeds of homotopy. Homotopy theory, and it sort of doesn't. Somehow, in some sense, it doesn't make sense for disconnected sets. But right? And even the topologists can't agree on this thing, and they just say it's the wrong question. So we'll just say that yeah, we won't apply the term simply connected or not simply connected. We won't even decide on this unless we're talking about a domain, right? So we're only going to talk about domains when we say simply connected, not simply connected. So only connected open sets. All right. So simply connected domains give, or at least on simply connected domains, you get Cauchy's theorem without, any, any extra condition on gamma, right? If you have a simply connected domain, U and a holomorphic function on U, and gamma is any cycle in U, then the integral of f around gamma is 0, right? And well, it's sort of obvious, right? If U is simply connected, then any gamma is homologous to 0, right? That's the point of simply connected, right? So we have that the winding number is 0 for all points in the complement, and so Cauchy applies to that gamma, right? It's kind of a special case, but it's sort of a nice statement. Now, if we have Cauchy's theorem, we expect primitives, antiderivatives, right? So let's prove this. So if we have a simply connected domain and a holomorphic function f, then f has a primitive in U. So f has an antiderivative. All right, so let's fix some point in P. And notice that U is connected, therefore it's path connected. And actually, we can take that path to be some piecewise C1 path or even C1 path if we want it. So for every Z, every other point Z in U, we pick a gamma from P to Z, and we define this capital F, that's going to be our primitive, as the integral of f over this gamma, right? So at this point, for every Z, there is a fixed gamma, right? So it's kind of a complicated definition, but we have a definition of a function in U, right? Now, if alpha is any other path from P to Z, C1, piecewise C1, right? Then we apply Cauchy, because if we look at the difference of the integrals, that's the integral of the difference, and gamma minus alpha is a cycle, right? And so it's a cycle. We apply Cauchy's theorem to the simply connected domain, so it applies, and we get 0. So the difference is 0. So the upshot is that this definition does not depend on the cycle that we take. Oh, sorry, the path that we take on the gamma, right? We can take any path that we want, right? And this is the key point. Why does Cauchy's theorem imply primitives? Because with Cauchy's theorem, you get, if you have Cauchy's theorem for all cycles, then you get path independence, and path independence gives you primitives. All right, so we have this f, and we want to show that it's the primitive. So now it's well defined. Doesn't really matter what path we take. So consider some q in U, any q, and let gamma be a path from P to Q, and take a disk around Q that fits in U. All right, so we have the following picture. Right, U is something, and then we have the disk in here. So P and Q are going to be, well, P is already fixed, and Q is some fixed point now, and we have this entire disk is in U, right? And so for any z in the disk, we have, because f is independent of the path that we took, we could take the path from p to z to be gamma plus the straight line interval from q to z, right? And so that's giving us our f. Now we can rewrite this, right? We can write it as the integral over gamma plus the integral over this straight line segment, right? And the first term, this guy, that's constant, right? As z moves in this disk, right? So this is precisely how we define the primitive in a star-like domain. So in this case, in the disk is a star-like domain. So we've already proved that it was a primitive. It's a primitive here, right? So it's the antiderivative locally, and we have that it's well defined, right? That's it, right? We have once you have it well defined, then you only need to show that its derivative is little f locally, right? And we've already done it in this little disk. All right. So let's look at some corollaries. So if we have a simply connected domain and a function which is nowhere zero, then there exists a holomorphic function g. Basically, it's the log, right? Or we're taking the logarithm of f, right? So there's a function g such that e to the g is f, right? For example, if we have, let's suppose that I have a simply connected subdomain of c minus 0, but U is simply connected, right? So it's not all of c minus 0 that's not simply connected. Some simply connected open subset, so open domain, right, of c minus 0. Then there is a holomorphic function L such that e to the L is z. It's a branch of the logarithm, right? So that would be an example here, but really, we can do this with any non-zero f. Here it's z, and that's why we're taking a subset of c minus 0, because that's where it's non-zero. Okay, so let's prove this. I look at f prime over f. That's holomorphic, right? F is nowhere 0, so I can divide by it, no problem. We can find a primitive. Let's call it g, right? It's actually going to be slightly different than this g. But, so we'll find a primitive for this guy. And, all right, so let's look at the quotient of e to the g and f. Let's see how they're related if we divide one by the other. F is non-zero. This just makes perfect sense. Let's take a look at the derivative of this. Well, just, quotient rule, right? And you get this mess over here over f squared, right? But now, if you look at this over here, g prime, right? That's a primitive, right? What is it a primitive of? This guy, right? So if I look at g prime, I get f prime over f. Well, if I get f prime over f, then multiplying by f gives me f prime, right? Okay, so I have this f prime over here. Well, notice that that's the same thing over here. So it's just 0. All right, that means that e to the g divided by f is constant. I don't know exactly what constant, but it's constant. It's some constant. All right, well, that means that e to the g is a constant times f, right? And that constant is non-zero. I can write this constant in a different way, and basically add something to g, add some constant to g. So I can write f as e to the g plus some c, right? And that's what we wanted, right? So maybe it wasn't quite g, but it was up to a constant. It was the right g, right? That we were looking at here. All right. Now, if we have the logarithm, we can also take roots. We can basically, take any sort of, any sort of exponent. So in particular, roots. So suppose that we have a simply connected domain and a nowhere zero function, which is holomorphic, and some, any natural number k. Then there is a holomorphic g such that the kth power of g is f, right? So g is one of the kth roots of f, right? So how do we find this function? And this g is defined on U, right? It's holomorphic on U. It's not just locally. This is defined on U. That's the whole power of this being simply connected. So, well, we can get logs, right? So find a c such that is true. E to the c is f. And now define your g as e to the 1 over k times c. And I claim that's the right g. Well, let's check. G to the k. Well, let's plug in the definition of g, right? And laws of exponents. And we get e to the c, right? Well, e to the c is f, right? So, all right. So once we have simply connected, we get Cauchy's theorem, doing working on any cycle. Once you have Cauchy's theorem working on any cycle, you get primitives. Once you get primitives, you get logarithms. Once you get logarithms, you get roots, right? So that's basically what we've done today, right? So we're gonna look more at simply connected domains next time. So all right, so see you then.